Hello students, I want to talk about the quadrilateral family tree, and this is for a couple of important reasons. One of the biggies is we adopted a new book and they take a quite a bit different approach to the quadrilaterals than what I'm going to be teaching in class. The bottom line though is I'm going to expect you to follow what I'm about to show you as far as definitions and the sometimes always nevers that you may encounter. And also, this may be contrary to what you've experienced in the past with previous teachers. Doesn't mean that they were wrong, it's just that they took an approach that may be a little easier to classify rather than to dig deeper into the formulas. And since this is a very formulaic approach on what we're going to be doing in these classes, I'm going to show you some of the reasons why I'm going to follow this family tree. So let's go ahead and take a look at it. This may look scary at first, but it's not too bad. We're going to spend most of our time right here on the convex quadrilaterals. Now again, a quadrilateral is basically any polygon that has four sides. Every now and then we'll refer or explore maybe a convex, but a concave, but a convex is basically given any 2 points, we can draw a segment AB to where all the points contained within that segment are on the interior of the figure. So this breaks off into 3 branches. We have the cyclic, the trapezoid, and the scriptable. I call this the tangential quadrilaterals. So the cyclic quadrilaterals is simply given a quadrilateral, the vertices all lie on a circle. So that circle basically circumscribes the object. The inscriptable or tangential is every one of these sides is tangent to a circle that is inscribed on the inside of the quadrilateral. And then we have the trapezoid family. Now the trapezoid family is probably what's going to throw you off because I'm doing it quite a bit differently. To me, a trapezoid is a quadrilateral with at least one set of parallel sides. Let's get started. Starting with the cyclic quadrilaterals. This is going to be pretty big in this course because this is a circle-based course. When we look at the cyclic quadrilaterals, we're going to start off with actually triangles. So when we do the triangles, we have a set of 3 non-collinear points forms a triangle. And a set of any 3 non-collinear points always forms a triangle, and every single triangle is cyclic, every single one of them. And we're going to be looking at all the formulas that apply toward a triangle. Now, one of those formulas is called Heron's formula that we're going to play with. Now, Heron's formula is just a fancy way of finding the area given the sides. But imagine this. If we made a triangle and we had 3 sides, there's a 4th side up here with 0. But if we suddenly make that side lengthy, we have ourselves a quadrilateral, and this is a cyclic quad. Again, all 4 vertices are on the circle, and the circle circumscribes it. Going back to triangles, when we dissect the triangles, we're going to be looking at incenter, circumcenter, all kinds of stuff. And those definitions apply to a cyclic quad. The cyclic quad, and this is how the family tree works, goes down to the isosceles trapezoid, again all the same properties, to a rectangle, to a square. So these 4 objects are what we're going to classify as cyclic quadrilaterals. The next one is tangential quadrilaterals, also called inscriptable. It just depends on the teacher and what part of the country they come from. So a tangential quadrilateral is I'm taking a quad and all these segments, they are all tangent to the circle that is inscribed on the inside. And again, this goes back to circles, and we're going to explore some of this with triangles at first when we look at incenters of a triangle. That's coming up pretty darn soon. So all 4 of these are tangent to the circle. Underneath the tangential quads is the kite, the rhombus, and the square. The square shows up. The square is a very, very popular figure. So we're going to look at each of these in turn. Our next family tree is the trapezoid family branch, and this is the one that's probably going to throw a few people off. Not just students. There's still teachers all across the country that are still debating this, and it doesn't help when textbooks confuse teachers by someone saying exactly one set of parallel lines versus at least. Now let's take a look at Math Open Reference. I've sent you to Math Open Reference many times. So let's take a look at the trapezoid right here. And this is what I'm talking about. There's a lot of formulas involved in a trapezoid. We have the mid-segment, we have the area, we have diagonal relationships, so on. We have at least one set parallel right here. Okay? So again, a quadrilateral, at least one pair of parallel sides. So right now we have a trapezoid. Trapezoid, trapezoid, trapezoid. I kind of made this 90 degrees right here. And we're getting up to 89 degrees and we're still a trapezoid. Then right here, and you're going to learn more about limits in pre-cal, but this is basically an introduction to limits. We get to 89.9, 89.99999, and then poof, 90 degrees. Well, I've created myself a rectangle is what I did, but the definitions, the guts of the definitions still apply. Nothing changed about the definitions of a trapezoid. It's still a trapezoid. And when we go to 90.001, trapezoid again. So it makes no sense mathematically to say this is all trapezoid. Bingo, not trapezoid. Then trapezoid again. Nothing changes on the diagonal relationships. Nothing changes on the mid-segment. Nothing changes on the area. It's all trapezoid. So going back to this, we have the trapezoid family. Look at this. Sometimes is green, always is blue. Therefore, a parallelogram is always a trapezoid. A rectangle is always a trapezoid. A square is always a trapezoid. Now over here we got the rhombus, which a kite, once the sides become, both sides become equal, is also a parallelogram. Now the isosceles trapezoid, which is cyclic, has some different properties, additional properties. I wouldn't say different, additional. They still have all the properties of a trap, but now they have the cyclic properties. And the cyclic property carries on through here. So the square, rectangle, and isos still fathers back up to the trapezoid. So a parallelogram is always a trapezoid, but a trapezoid is sometimes a parallelogram, because what we do for the parallelogram is we put additional restrictive definitions on it. All opposite sides have to be parallel. So that's a restrictive to that. So only some trapezoids are parallelograms. Rectangles have further restrictions. The interior angles are now 90 degrees. So we have perpendicular relationships on these sides. So some parallelograms are rectangles. And then we have further restrictions on the square, where some rectangles are squares. Again, sometimes is green, always is blue. Let's move on to the kite family branch. Now the kite is another special character, special hard to describe object. Straight up, it's with two distinct pairs of equal adjacent sides. Now we're talking, when we talk about distinct adjacent, we're talking about this side and this side from vertex A. And these are going to be the same. Now the properties of a kite remain constant, but as soon as I start to do things, and I can try and make, well, it's going to be very hard to make into a square based on this picture, but there we go. Now I've just made myself a square. 90 degrees opposite, we have congruent and congruent, therefore these are all 90. I just turned this kite into a square. I also turned it into a parallelogram, because we can prove same side interior angles are congruent, so on and so on. I mean, supplemental. All kinds of things. So the definition doesn't change just because I moved the sides around. Everything on the guts of it is still is tangential. Now, that means they have an in-center, in-center, and in-center, which will become more clear when we do the triangles. So we have the kite family tree, we have the trapezoid family branch, and it all comes together in this right here. Those are the big differences that is going to be in the class. We're going to discuss this when we hit triangles and when we hit specific quads. You're going to be doing proofs, constructions, so it'll all make sense. But the reason for this video again is that the book has different definitions and other teachers have gone different routes on this. But for my class and my students, this is what we're doing. Alrighty, I'm going to get this posted and call it a day.